Recently, I've been looking for ways to use Mathematica, and I work on Wall Street, and a very popular database product there is KDB. And so I'm going to talk about a little bit about KDB, but really this presentation is about how I want to avoid using KDB natively and how I want to program in Mathematica and translate Mathematica code to the Q language, which is what you program with in KDB, and make that all transparent, and what my motivation for doing that is. KDB is a highly scalable column, what's called a column-oriented database, and it's used in Wall Street because it easily processes massive volumes of data. Market data streams into these computers, thousands of messages per second, and all this data is captured in real time. And there's not one Wall Street firm that I know of that doesn't use KDB because it seems to be the only product that can keep up with it. So it's an in-memory database and it has a 64-bit version, and it can handle huge amounts of data. It has its own programming language, which originally was called K, which is very, very cryptic language. And in later versions, they came out with a higher level version of the language called Q, but Q is really syntactic sugar on top of K, so K is still there, but you program in this sort of higher level language. But Q is still very cryptic and somewhat difficult to learn, but it also has an SQL-like syntax, which is, again, just another layer of syntactic sugar on top of Q. So really everything, like all computer languages, compiles down to this very low level language. So why is KDB faster than a relational database system? So most relational database systems are row-oriented. That's the way the data is physically stored on disk. So when you can imagine when you're pulling data, even if you're only interested in column 2, you have to pull out whole rows. And there's various optimizations that databases do, but KDB is fundamentally column-oriented database, so the values are stored in memory as column vectors. And you can imagine if you're doing analysis as opposed to like transaction processing, that has a major advantage because if I'm only interested in certain columns, I don't actually have to pull all that data. And another unique thing about KDB is a very small size, and it fits very well in a cache. The whole executable is just 234 kilobytes, which is fairly small these days. So just to give you a flavor of Q, the Q language, here's sort of a mapping between some common Mathematica expressions and their Q equivalent. So Mathematica uses curly braces for lists, Q uses parentheses, but you can also have sort of flowing across the screen. If you have a uniform data type, you could just use spaces, but you could also use semicolons optionally. Some operations, Mathematica has first, Q also has first, but you don't need any syntax, no brackets or anything, you just say first of list. But you can use optionally brackets or parentheses. And down the line, at some level there's sort of a one-to-one correspondence in various parts of the language between Mathematica and Q. So you can see what I'm getting at. It's not that hard to translate a subset of Mathematica to Q. And this is just an example of what a Q program looks like. And this is not even a very cryptic one because it basically uses their SQL syntax. But what this is doing is pulling two CSV files, merging them, and then writing them out again. But I wanted to avoid having to write that. So KDB represents tables. So if you're literally going to create a table, you might write something like this. And this is the supplier parts database that's always taught in database courses. So if you have a bunch of suppliers, and the way this red highlight here shows how you create a keyed table. So this is basically saying I have a table I'm calling S, and the first column are the keys. That's what's in the brackets, and the keys are S1, S2, S3. Those are the supplier numbers. And then another column is the name, and the names are Smith, Jones, and so forth, and so on. And then, you have the parts similarly, and then the supplier parts table. And a typical query that you could run in Q is just select from S, and that would give you some output that look like that. Continuing with that, you could also, like SQL, you could say where, and you could have grouping using by, but it's not ANSI SQL. There's lots of subtle differences, so you sort of have to learn that as well if you want to use it. So the real question is, how can you use Mathematica and KDB together? There's a jar file that you can download from KDB's, KX is the name of the company, kx.com. You can download a jar file. And so you can use JLink to link Mathematica with KDB. So I'm going to do that now. So so the first step is sort of to initialize your Java environment. And that's that. The next step is to launch, you could launch KDB right from, you could launch it separately, or you could launch it right here using link launch. And you have to run it on some port. So I'm going to do that. So that launched KDB. And then, like if you've used JLink before, the object that you need to create, KX systems like to be very terse, so the object you need to create is called C. And so we're going to create a C. But I assign it to variable Q to remind me I'm working in the Q language. And then just to test that connection is set up, I'm going to tell KDB to add 1 plus 1. And I get 2, so I know that my connection to KDB is good. So that evaluation happened in KDB, not in Mathematica. So you can think of KDB in this case as being an alternate kernel, which is the idea of this. It's an alternate kernel that's optimized to do certain types of high data volumes. So here, I'm going to do the supplier parts database first here, just to give you a flavor. And this first line, I'm basically telling KDB to load this sp.q program, which is the supplier parts database demo. And then I could run this query. I'm going to select all the rows in the SP table. And because this is Java link, you're going to get back this Java object. But of course, you can inspect that object. And you can find out that it has these two fields called X and Y. Again, this is the way they cryptically encode things. And then, you could say, well, what is X? And you can look at that. And it turns out X is the column names. And that would leave you to believe that Y is the actual data. So now you could write functions, which I'll show you later, that hides all this X and Y stuff. You don't have to worry about it. You can also see the methods supported by that Java object that got returned. And one of the interesting ones here is @. And so you could also pull out specific columns. So here I'm going to pull out the P column, which are my part numbers. And then you could start obviously you can mix Mathematica operations on this object that returned. And so here I'm just mapping add across two column names to get both the supplier IDs and the quantities. And of course, you can then do anything you want, take a total, for example, of that. But why go through all this trouble at all? And the reason is because KDB can process large volumes of data much better than Mathematica could. And for this demo, I'm going to, so the goal here is to take some market data. This is actually simulated data. It's not real data. I actually created the data in Mathematica. And so the data just has a time, a name of an exchange, a stock symbol, a bid price, a bid quantity, an ask price, and an ask quantity. And the problem here is I actually want to group, so I want to do a group by on that data by hour. I want to group the data hourly, and then by exchange and by stock symbol. And then within that group data, I want to compute the min, the mean, and the max of the bid and the ask prices, just to do analysis, just to see the hourly variation in prices. So in this first step, I'm going to tell KDB to load this quotes.big.csv file. So all my data is in my CSV file, and this is 10 million rows of data. So it's quite a lot of data, but that's actually small from KDB's point of view. It could do much better than that. Now, loading the data is still type of slow. It has to pull all the data into memory off disk, so we're going to wait about 30 or so seconds for that. So I'll take some questions if anyone has.
How much memory are you using?
So right now I only have 4 gig on this laptop, but obviously with KDB 64 you can go up to monstrous amounts of memory.
It only runs in memory?
No, it does go out to disk if it runs out of memory. So, and there's various optimal ways to go. They have these optimal ways of storing, because they store the data at columns. You could actually specify that all those columns get written to separate files, and so you can do all these optimizations where you could actually write data out very quickly because you're writing it out to separate devices even. So that looked like it's done. So what that quotes program did was actually did 2 steps. It loaded the data and computed the grouping. Let's look at that in table form. Now you can see the way the data came back. It came back column oriented, so you could do a transpose on that. In that span of time where really 80% of it was loading the data off of disk, it did a group by on this data to get hourly slots for Arca and Apple, and that's just that's the key part, and the actual data is here. That's this result. And of course you can combine those two. So here I show a little join where you can see the full set. So when you do a join operation in KDB, you actually get a keyed table back, and the keys are are your grouping columns. So I grouped on the hourly component of the time, on the exchange, and on the symbol. And then the other part is the actual result, which contains my min, bid, mean bid, max bid, and there. And so you can just join those together within Mathematica to show the data like so. Now, if you tried to do the operation in the most obvious way in Mathematica, I did this on 10 million rows of data. It runs overnight. So you can see the power of doing this. So let's just go back to the presentation then.
Storing the data how? When you did the join? Storing the data also in KDB?
So right, so when the join happened, data was in memory. So it did the join in KDB, and then the results came back over MathLink back to the Mathematica kernel. So the idea here is you want to get to the point where KDB is doing all the heavy lifting in terms of the data processing. The data is coming back to Mathematica in a much smaller format, so you've done some grouping operation, and now you can go on with your life and do further analysis purely within Mathematica.
It's really asking, so the overnight job, you use Mathematica by itself to read the data in raw form and then do some kind of Mathematica join?
Yeah, well, I wrote some code in Mathematica. The data was already in memory, so what I actually did, I'm not even counting the time of create. So I wrote some simulator that simulated the market data. So we got to the point where he had all the data. And then I timed the actual operation. Of course, I did it in a very, I did it using, gather by and then computing the means and stuff on the gather by results, which is not the most efficient way to do it. But it is the most obvious. And the idea is, in KDB, you're using the most obvious way to do this, but it's happening in seconds versus, so I'm sure if I optimize that program in Mathematica, I can get it down to, it's not an overnight run. But if you got up to, you know, hundreds of millions or even billions of rows of data, it's just, you know, you're not going to get anywhere in Mathematica. It's not really what it's made for. KDB also, yep.
If you were, what you would normally do with this data is have it in some kind of database, but not necessarily KDB.
Yep.
How would KDB's join time for this compare to SQL Server?
It's significantly faster. So what I say, I mean, relational databases don't have their purpose, and they're really good at transaction processing, for example. So if I was building a website and I needed order manage, you know, I was using a web front end for a e-commerce thing, relational database is great. But when you're doing data analysis, KDB, just relational databases just can't compete with this type. The other thing is when you have data streaming in real time. I mean, you might not have that in your scientific application or something, but or maybe you do because you're taking measurements off of a lot of devices. It can handle the real-time streaming in of data and the simultaneously querying, because that's what we're doing in Wall Street with market data. You have market data streaming in, but yet you have all these queries happening all in real time, and it holds up. So that's all well and good, but you know, it involves, there's some learning curve, and there's some problems with learning Q. You know, it's not the official, first of all, the SQL part of Q is not official SQL, but that's not a big barrier. But then there's also the Q programming language, and KDB gives these very cryptic error messages when things go wrong. So what I really want to do is program purely in Mathematica. And what I've begun to do, and it's not complete, is write a Mathematica to Q translator. And the simple stuff is really easy. There's direct mappings for list processing, like first, rest, most, and so on, maps very easily onto the Q language. And other things map less easily, but they're doable. So I could show you some examples here. Here's a test program that tests my translator, and I'm doing very simple things. I'm checking. So I have this function called toQ, and it takes a Mathematica construct. Here it's just an empty list, and make sure I get back the Q equivalent, which is an empty, you know, list as parentheses, and so on and so forth. Here's one of the idiosyncrasies about Q is that it's funny, you can create a list very easily of any size, but if you want to create a list of size 1, you have to actually say enlist, and that's because there's an ambiguity with when you use parentheses between, are you really talking about something in parentheses or you're talking about a list? So you have to have this. So these are all the quirks in Q that sort of annoy people. So this translator would take care of all of that. And I could actually run this, this program, and you know, it ran these 8 tests, and they all passed. And that just shows I converted the Q to the KDB, I'm sorry, the Mathematica to the Q syntax, and it all worked. The more interesting thing is how do you do in Mathematica things that just don't have a representation in Mathematica? So Mathematica doesn't have a table representation of data, and so I also created those features in Mathematica that you could use to prototype. So if you're prototyping, you're not really doing mass data processing yet, you could work completely in Mathematica, not have a Q using these functions. So here I make a table. Call these tables, and so this is completely Mathematica code. So I'm emulating Q in Mathematica without any need to actually connect to KDB. So you have tables, and you could look at them in tabular form. You could do, you can extract rows, and you could do queries all within Mathematica. So there's my syntax for doing a query where I'm selecting the status column from my supplier table. Here's with a distinct, and there's a where clause. So I have this sort of sub-language within Mathematica that you can program in. And then you do Q code generation on that. So I could take my select and translate that to Q's version of select. And I also have an execute. So you can execute the Mathematica, and what it does is does the translation, ships it out to KDBs, and gets the result back all in one step. So the entry point to actually doing this yourself is quite low, because KDB actually gives away their 32-bit version, which is not going to do your heavy lifting with lots of data, but you can play around with the 32-bit version. And I will make my code available at some point. I just have to clean it up a little bit. You can email me. You could look for that code. It's going to be up on my Mathematica cookbook site. But you can email me if you want some version earlier. And the thing about the 32-bit version, just two downsides, is that it sort of expires every 2 months, and so you have to re-download it. And it also times out. So if you have a really long-running problem, you can't run it for a long time on the free version, because it'll just time out in the middle. The downside of KDB is that the commercial version is very expensive. It's like starts at $25,000. Hence, Wall Street can afford it, and individuals can't. But if you're doing, I've talked to them, if you're doing a purely research or academic thing, you could usually talk to them and they'll work something out. And I'm also toying around with the idea of setting up a sort of a cloud computing environment that combines this Mathematica and KDB. And if there's any interest in that, talk to me or email me, and we can talk about that.